Hi guys, today we're going to be looking at group 7, also known as the halogens. So by the end of this lesson you're going to be able to give the properties of the halogens, including their physical appearance. You're going to be able to explain how the properties relate to the outer electrons, just like in our previous video, and going to be able to explain how the properties change as you go down the group. So very similar objectives to last lesson, except we're focusing on group 7 rather than group 1. So, starter, we've got 3 questions, although this last one will take you a little longer, so give yourself 5 or 10 minutes, have a quick go at those. Okay, let's go through some answers. So, give 4 properties of a non-metal. So, any 4 from dull, not sonorous, soft, brittle or gases, low density, low or no tensile strength, low melting point, poor or no thermal conductivity, poor or no conductivity. So any 4 from those properties, that's perfect. Describe the arrangements of particles in a gas. Well, they're far apart and they're able to move freely and rapidly. So they're all whizzing about with loads of space in between them, and they're not all bound together. They're able to move rapidly away from each other. Okay, now this last one. By drawing relevant diagrams, explain why lithium is more reactive than neon. So what we're getting at this is we're looking at the electronic configurations, showing that our neon has a full outer shell, so it doesn't like to gain or lose electrons, whereas lithium, it's got that 1 electron in the outer shell that it really likes to get rid of. So let's see how we can word that fantastically and what our diagrams should look like. So our first mark is for drawing a diagram of the electronic configuration of lithium, which has 1 electron on the outer shell and the rest of the structure correct. So that would be 2 electrons on the inner shell, 1 on the outer shell, because it's got 3 electrons in total. Our next mark is for drawing the diagram of neon's electronic structure with 8 electrons on the outer shell. That's for 1 mark. And then the rest of the structure correct. So this would be showing, again, just 2 electrons on the inner shell, 8 electrons on the outer shell. So then we need to explicitly say that lithium is more reactive as it has 1 electron in the outer shell, which can be easily lost to form a positive ion. So this idea that the electron can be lost, that's what makes it more reactive, because it likes to lose that electron. Whereas neon has a full outer shell, so it does not like to gain or lose electrons, so it's not going to form any bonds. Okay, task for you. Pause the video here and draw the electronic configurations of fluorine, chlorine and bromine. Tell me what do they all have in common, and tell me what group are they all in. So pause the video here, give yourself about 5 minutes to give that a go. So here's our answers. Is fluorine, chlorine and bromine. Fluorine 2 on the first shell, 7 on the second or outer shell. Chlorine 2 on the first shell, 8 on the second shell and 7 on the third or outer shell. With bromine, 2 on the first shell, 8 on the second shell, 8 on the third shell, 7 on the fourth shell, which is also the outer shell. So you notice the thing that's the same is that they all have 7 electrons in their outer shell. So they've all got 7 electrons in their outer shell and they're all in group 7. So remembering back to last lesson and the lesson before, it's this idea that the number of electrons in an atom's outer shell is the same as the group number that it's in. Okay, so these are all group 7, they'll all have 7 electrons in the outer shell. So here's group 7, it's on the right hand side of the periodic table, meaning that they are all non-metals. And this is what they look like. So we've got fluorine, chlorine, bromine, iodine and astatine. Just like that. Now what are the properties? Well, so chlorine's a dense pale green gas, smelly and poisonous, and it's often in chlorides. So sodium chloride in the sea, or table salt also has chlorine in, because it's sodium chloride. It's melting at boiling point, we'll look at that in more detail. Bromine is a red liquid, red-brown vapour on top of that, so it boils quite easily. It's smelly and poisonous. It occurs as bromides. Iodine is a grey solid with purple vapour, smelly and harmful, and occurs as iodides. So, what do they have in common? So they're all non-metals, which we spoke about a couple of slides ago. They do not conduct electricity. They've got no delocalized electrons. They cannot conduct electricity. They're all brittle and crumbly when solid, and they're all poisonous and smelly. In fact, chlorine is so poisonous it used to be used as a chemical weapon. So it's very, very toxic. So they all become darker as you go down the group. So fluorine is a pale yellow, going all the way down to iodine, which is very dark grey. Chlorine's green, bromine is a dark orangey brown. So we're getting darker in colour as we go down the group. Okay, so what I'd like you to do next is have a look at the pictures of each of these different halogens, and you tell me what are the trends or patterns that you can spot. And a hint is, what's the state of matter they're all in? So write yourself just a very quick sentence about that. What trends do we see, especially about what state of matter they're in? Okay, so as we've already said, group 7 elements get darker as you go down the group. So what colour would you expect astatine to be? Well, you'd expect it to be darker, wouldn't you? So going back to the trends that we see, what we actually find is that it gets more solid as you go down the group. So we start off with fluorine and chlorine that are both gases at room temperature. Then bromine becomes a liquid at room temperature, and iodine is a solid at room temperature. So the melting and boiling points of the halogens increase as you go down the group because the molecules get bigger, and we're going to talk a little bit more about that in a second. Oh, just one point of interest. So room temperature is 20 degrees, okay? So for the first two elements here, you can see that 20 degrees is a lot higher than both the melting and the boiling point of fluorine and chlorine. So these, well, that's higher than the melting and boiling point, so it will be a gas. Now with bromine, 20 is in between -7 and 59. It falls between the two numbers, so it will have melted, but the temperature's not high enough to boil it yet. It needs to be 59 degrees before it will boil. Then with iodine, both the melting and boiling point are considerably higher than 20 degrees, so it's not hot enough to melt or boil iodine at room temperature, so it's a solid. Okay, right, so like most other non-metals, the halogens go around as molecules, so they don't just exist on their own as individual atoms, they exist as molecules. Okay, now these molecules are diatomic. So diatomic means it's got two atoms, because di means two. Okay, so if you have a diatomic molecule, it's got two atoms in it. So if chlorine, bromine and iodine are all diatomic, they look how I've drawn it at the bottom of this slide here. So they're joined in pairs as Cl2, I2 and Br2. Okay? So not like individual atoms, they go around in pairs. Like that. Okay, now what this slide is going to be about is the difference between intermolecular forces and intramolecular forces. This is a bit of a difficult one, so please feel free to watch this section as many times as you need to. So, between the actual atoms in chlorine, there are strong covalent bonds. So if we look at this diagram on the left, I've drawn a line to show the strong covalent bond between the chlorine atoms. They're very difficult to break. They don't break very easily. And these are called intramolecular forces. Now, between the molecules, there are these things called intermolecular forces. And these are very, very weak. Okay? So an intermolecular force is a force of attraction between molecules. Right? And that happens between all molecules, and they're always very weak. Okay? So very easy to break, which means that chlorine will have a low boiling and melting point, because this is what breaks when we boil and melt something. It's these intermolecular forces. Now, importantly, these strong covalent bonds do not break when we melt or boil chlorine. It's only these weak intermolecular forces. Okay, so strong covalent bonds, they're difficult to break. They do not break when we melt or boil. These weak intermolecular forces, they are very easy to break. These do break when we melt or boil. Okay, there's this video as well if you need another perspective on that. It's about a 3-minute video kind of summing up what we've learned so far. Okay, pause the video here, give yourself some time on these questions. Okay, so from what we know about the halogens, what properties do you predict astatine to have? Well, we predict it to be a solid with a very high melting and boiling point, and we expect it to be a very dark coloured solid. Now explain why the melting point of iodine is higher than fluorine. So, if the melting point is higher, it must have greater intermolecular forces. So iodine has greater intermolecular forces between the molecules, which makes it harder to break, so we need to put in more energy to break them, so it's a higher melting point. Okay, so as we go down the group, we get much less reactive. So iodine is not very reactive at all when reacted with hydrogen, even if we heat it up to 500 degrees C. Whereas fluorine, if you put it in with hydrogen, it reacts instantly, even at minus 200 degrees. So it's very, very, very reactive. Fluorine is one of our most reactive elements for sure. So how will astatine react? Following that trend, how will astatine react? Which is it's further down the group than iodine. So how will that react? Well, the answer is it pretty much won't. It's a very unreactive element. Okay, so why does the reactivity decrease? So this effect is the opposite of the alkali metals. Okay, because remember, with the alkali metals, as we go down, it gets more reactive. Now, the biggest, most important thing to remember is that fluorine, chlorine and bromine, when they react, want to gain an electron. Okay, so we're going to keep that in the back of our mind throughout this whole explanation. They want to gain an electron. So the atoms of each element get larger as we go down the group. So that means the outer shell gets further away from the nucleus and is shielded by more electron shells. So what that means is it gets harder to add on that extra electron it's trying to gain, because it doesn't feel the attraction from the nucleus if there's a load of electrons in the way, effectively blocking or shielding all that positive charge from the nucleus from being felt by that outer electron. So yeah, again, the further the outer shell is from the positive attraction of the nucleus, the harder it is to attract another electron to complete the outer shell. So it's quite easy for fluorine to gain that extra electron, because the extra electron is coming in quite close to the nucleus. There's not very many electrons between that electron and the nucleus. Whereas with bromine, to add an electron onto the outer shell, it's really far away from the nucleus. There's lots of electrons in between, and those shield the electron being added from feeling the attraction to the positive nucleus. So that's why the reactivity of the halogens decreases going down group 7. Okay, so given that explanation, feel free to watch that as many times as you need to. Got an exam style question here. I'd like you to try and describe and explain the reactivity of fluorine. Pause the video here and give that question a go. Okay, so any 3 statements from this list, you get 1 mark for each. So first of all, fluorine is the most reactive halogen, so we're describing the reactivity of fluorine, saying it is very reactive. Because remember, if we're describing, we've got to say the what. So that's the fluorine is the most reactive. Now describe and explain. To explain it, we need to say the following points. We need to say the why. So it's because fluorine reacts by gaining an electron into its outer shell. Fluorine has a small ionic radius, so the distance between the nucleus and the outer shell is less, therefore fluorine attracts the electron very strongly. So there's not very much shielding, it's very close to the nucleus. Now always in exam questions, they're much more interested in you talking about the ionic radius than mentioning shielding. It's always a better shout to talk about the ionic radius and how close that electron is to the nucleus. Okay, so the halogens can react with group 1. Now when they do, they form salts. So we see reactions like potassium plus chlorine forming potassium chloride. And here's its simple equation. Now because chlorine is diatomic, we always, when we put it in chemical equations, write Cl2, which means we have to think about how to balance that. So if we have 2 chlorine atoms and we're forming KCl, we must need 2 potassium atoms in order to balance that equation out. Okay, now they form an ionic bond because obviously group 1 elements are metals, group 7 are non-metals, and if we have a metal reacting with a non-metal, it forms an ionic bond. Okay, pause the video here, see if you can draw the dot and cross diagram for KCl. This is a bit of revision from the C2.2 module. Okay, and it looks like this. So we show the outer shell of potassium empty because it's given its electron to chlorine, and we represent that electron as a dot to show that it's different from all the other electrons because it's come from potassium. It's not different in any other way. Obviously all electrons are exactly the same, but we draw it as a dot to show that it's come from potassium. Then we've got 7 crosses, which are the electrons in chlorine's outer shell to begin with. So we draw a plus on the potassium because it's lost that electron. We draw a minus on the chlorine because it's gained the electron. They've both got full outer shells. So there's our dot and cross diagram. Okay, so a bit more of a tricky idea now. So more reactive halogens are able to displace less reactive halogens. Now I'd like to write this definition in your books. Displacement is a reaction that occurs when a more reactive compound replaces a less reactive displacement is a reaction that occurs when a more reactive element replaces a less reactive element in a compound. So for example, we know that chlorine is more reactive than iodine because it's higher up group 7. So if I put chlorine in with potassium iodide, the chlorine is able to kick the iodine out of the compound it was in, and it'll form iodine on its own. So if you watch this animation at the bottom, we've got the chlorine, it's able to come in and replace the iodine in a compound. So it can bond with the potassium rather than the iodine. And it does that because chlorine is more reactive than iodine. Okay, some questions for you. So pause the video here, have a go at those. Some more questions. Okay, so we've got the answers attached as well, and we've got a plenary finally to finish off with. And if you've done all that, that's absolutely fantastic, and that's all for today.